theory which has come out of condensed matter. And this is largely joint work with Matai and Chuan Tian, my last research student. And they're both in Adelaide. And they've been working on this problem, a series of preprints here. Actually, some of them have been published now, and these pictures were taken from Journal of Physics Plus, which made a special feature on their work on biofermions, which is related to this, but which I won't talk about. And then I worked previously with both of them on other problems, and so the most of what I'll talk about this time is going to be from the joint work the three of us did. So a very rough outline is to explain what the tenfold way is in condensed matter physics, and then about topological insulators. I was taught to do this as a sort of colloquium style because I couldn't assume everybody was familiar with this. I've slightly toned it down and I make it very fast, since it looks as though most people are actually experts. So. And then I want to talk about two different ways of looking at the Ball compoundry. One more linked in with the physics, one more geometrical, and then how these two pictures actually tie together as T-duals, which I'll explain what a T-dual is, and then some speculation at the end on flux. So the story goes way back into the beginnings of modern quantum theory. There's Wigner's work in the 1930s and before on symmetries in quantum theory, the unitary anti-unitary theorem that if you want a transition probability preserving transformation of the projective Hilbert space of states, then it can be induced by a unitary or an anti-unitary operator on the Hilbert space. When he first did this, there wasn't so much application for anti-unitary, but a very important part here is played by the notion of time reversal, which has to be represented by an anti-unitary operator. And then he came back in the 1950s to use this for symmetry groups. And if you've got a symmetry group acting in a Hilbert space by unitary or anti-unitary transformations, so this is because you've got anti-unitarity, you've got to allow just for real structure on the Hilbert space. Shor's lemma says that if you've got an irreducible representation of the symmetries, then it's commuting algebra, the intertwining operators are form a real division algebra, and then Frobenius' theorem says that the reals are complexes or the quaternions. So you get a threefold classification. Then a few years later, Dyson looked at this classification, and in fact the explanation I've just given in terms of Shor's lemma and Frobenius' theorem is the way that Dyson produced to do it. But Dyson went a step further, that in fact there's a group of all symmetries, and there's a normal subgroup of those that are represented by unitary operators. And it turns out quite surprisingly that they independently give you a threefold classification. So immediately Wigner's threefold way splits up into 9 possibilities. And in fact, one of them, the middle one, complex, comes in two versions, as Dyson realised. So you get 10 different possibilities. There's also a connection between these and symmetric spaces. Dyson produced one symmetric space, didn't comment on it too much, but that was really the next step. Not much happened up until the 1990s, and then Martin Zierenbauer and Altland showed that actually all 10 of these things could occur in known physical systems. And they also made very clear the connection with symmetric spaces. So really the note about symmetric spaces is more due to Altland and Zierenbauer than to Dyson. And then there was a whole spate of activity through the next 20 odd years. And I just pulled it, one example of Kane with Fu and Melee. But the sort of climax of all this was a paper by Kitaev in 2009, in which he showed that everything could be fitted together, that the 10 is equal to 2 plus 8. 2 is the periodicity of complex K-theory, and 8 is the periodicity of real K-theory. And you get this kind of table. Down the left-hand side there are the Cartan symmetric spaces. There are 3 sort of discrete symmetries: time reversal, parity of the P, and then what in high energy physics is charge conjugation, but here is particle-Hall duality. And I guess parity here is more like chirality. So there are 3 discrete symmetries labelled there. If there's a 1, it means that yes, it's present, and t squared is 1, for example. If there's a 0, it means that that symmetry isn't present. If there's a -1, it means that, say, if you look at D3, t squared is -1 rather than +1. And similarly for the particle-Hall conjugation, and then chirality is either there or it isn't. So there are 0s and 1s in the third of those 3. And then you get different possibilities, different phases, and sometimes you just get nothing at all. Sometimes you get the integers. The integer quantum Hall effect is an example of that, where you discover that the conductivity, which I'll come to in a minute, is integer multiples of e squared over h cross. Or there's a Z2, which would be good for things like, say, superconductors. Either they're in a superconducting phase or they're not. So that's it. I put Altland and Zierenbauer there in quotation marks because it's usually referred to as the Altland-Zierenbauer table. But Zierenbauer is extremely unhappy about that. He says he doesn't want to be associated with this. Not that he doubts that it's true, but it's just that he thinks it's not quite right to put his name there. Anyway, so you can see the top 2 rows. You've got the periodicity period 2. The thing repeats as you go 2 steps to the right, and in the other one it would repeat further if we'd done a bigger table, but that's all you get basically with the periodicity 8. So why should K-theory be relevant to this? Well, you can really go back to another 1920s thing, block theory of solid state. You've got a configuration space with some dimension, it doesn't much matter what for these purposes, but it's got a crystalline symmetry. There's a repetition as you go through, you translate through the crystal lattice, and those commute with the Hamiltonian, and the Hilbert space decomposes into a direct integral bits, which are labelled by the dual, Pontryagin dual of the lattice group, which is a torus of the same dimension. You can also think of that dual as being the dual of the whole configuration space M hat factored out by the reciprocal lattice of things which are trivial on the crystal lattice. And the thing which is crucial here is that things are much simpler when you look at a particular value of K. And if you look at the Hamiltonian on the bit corresponding to K, then it actually just has a discrete spectrum. The ground state energy is non-degenerate, and only a finite number of energies are going to lie below the Fermi level, which is essentially what you've got in the energy available in your sample. So that you can effectively assume that that bit of the Hilbert space is finite dimensional. So it's sort of huge advantage. Incidentally, I mean, in one dimension, you can prove all this by Sturm-Liouville theory, and then there are just some jazzed up versions for higher dimensions. There are a number of papers by Barry Simon and various collaborators on this, mostly using variational theory. And one of the other things which in one dimension you sort of prove when you're an undergraduate is that everything depends continuously on the parameter. And that means that the overall Hilbert space, which is made up of these sort of pieces, can be regarded as a finite rank vector bundle over the set of K's, the dual lattice group. Okay, I mentioned the integer quantum Hall effect originally, because that provides another bit of motivation. Discovered experimentally first that if you have a magnetic field perpendicular to a plane sample at low enough temperatures, you apply a voltage in the direction shown, there's a current goes transverse to that, and the transverse conductivity, i.e. The thing linking the current and the voltage, goes in integer multiples of E squared over H cross. And I guess that's been the international definition of the ohm for about 25 years. There was a theoretical explanation of this first by Laughlin, but then a more interesting one by Fowles and collaborators, which interpreted this as being, well, interpreted the conductivity as being given by a Chern character. And, the T squared there is essentially the L hat that I had in the previous slide. That was modified by Pelissard, who realized actually there were a few problems with this, and they could be circumvented by working not with ordinary topology, but with noncommutative geometry. And there's a reason for doing the same thing here, because it turns out there's a symmetry in the Bloch parameters in many situations. If you interchange K and minus K, then you don't really change the physics significantly. And so, as well as having sort of, as it were, the functions of K, you've got this symmetry, and that means that you've got a something which makes the commutative algebra non-commutative. Okay, just a quick word about topological insulators, which is really what Kitaev and people were interested in. To the left, there are three pictures of what happens when you study electron motion in materials, and you can have the you sort of stop at a particular level, and the level is supposed to be between the blue and the yellow. Now that's the Fermi level, and then you've got a valence bond in blue and a conduction bond above that. And different situations can arise. In that one, there's a definite gap in the left. When you go to the middle one, the gap is sort of closed up. And so if you supplied a little bit of energy, you could knock an electron out of the blue bit into the yellow bit from being a valence electron to a conducting electron. But it can also happen that when you do have a gap, there can be extra symmetry at the edge of the material, which allows you to go across that gap. And that's supposed to be a picture, I'm afraid I couldn't find a good version of, on the right, that there's a blue bit and a reddish bit now as the valence and conduction band, and then there are some green linking bits. And they're things that electrons are allowed to do on the boundary, which they couldn't do in the bulk of this material. And all this sort of checks out with experiments. Okay, so what I want to do now is to move from, as it were, the physical background to look at this kind of problem more from the kind of Belisar perspective of using C-star algebras. And I put down that for these purposes, I'll think of C-star algebras largely as non-closed star subalgebras of bounded operators. Examples, important examples for this, the compact operators, the closure of the finite rank operators on the Hilbert space, and the triplets algebra, which I think we had last week. Well, it's an algebra on little L2 of the natural numbers, which is generated by shift operator. The fermions, I mean, I shan't need the detail very much, but the fermions I'm actually going to model, you can either use canonical anti-commutation relation algebra or a Clifford algebra of a real Hilbert space, depends which sort of formalism you want to use. They're essentially equivalent. And so the Clifford algebra is just generated by elements in the Hilbert space, but in such a way that the square of the operators is equal to the norm squared of the vector. I guess there should be times of identity there, but I have that. You can also think of the Clifford algebra as a twisted group algebra of a certain discrete group. And once you do that, you see it's got a canonical trace. And if you look at enveloping from Newman algebra, you get a type 2-1 situation. I promised I'd give at least one type 2-1 factor in here, just to match the topic of the workshop. You can use that trace to turn the Clifford algebra itself into a Hilbert space by using the trace and then closing it where it's pre-Hilbert space as I've done it, but you close up and get a Hilbert space. And so that's, you can then act with left multiplication, or for that matter, right multiplication. And then, again, just by way of explaining everything in case there are non-algebra, operator algebra people, the representation theory is quite important. So we'll say that two algebras are Morita equivalent if there's a natural equivalence between the categories of their modules. And as examples, the compact operators only have one irreducible representation, an obvious one on the Hilbert space from which they're defined. So they're all Morita equivalent to each other, and in particular to the one-dimensional Hilbert space version of the complex numbers. If you took functions from some locally compact Hausdorff space into the compact operators, that would be Morita equivalent to the thing without the compacts there. And I guess the other example, which in something to do with quantum theory you can't leave out, is that in finite dimensions, the quantum mechanical commutation relations have a unique irreducible by the Stone-von-Neumann theorem, so they're also Morita equivalent to those above. And then there's a standard kind of dictionary between geometry and algebra geometry and non-commutative geometry. The Gelfand-Naimark results, locally compact Hausdorff space corresponds to the commutative C-star algebra functions on it. Commutative C-star algebra has a spectrum which gives you a locally compact Hausdorff space. And then the Serre-Swan results that vector bundles over a locally compact space P correspond to the finite rank projective modules over the function algebra. And because they're finite rank projective modules, you have a set of projections coming, and they cover the things which correspond to the K-theory of the space. And so what one can do is define the K-theory of the algebra in terms of equivalence classes of projections. You have to allow projections not just in A, but in matrices of arbitrary size over A, and then you put on the equivalents. There are lots of ones which you can use, and which at least in this situation are all equivalent, although they're not always. But and then you can also define a K1 as well as a K0. I'm going at the moment to stick with the complex situation so that I just have periodicity 2, and I only need to bother with defining 2 K classes. And taking the continuous functions from the reals into an algebra roughly corresponds to suspension in the geometrical case. And necessarily Morita equivalent algebras have the same K-theory because they have the same representation theory, and therefore the projections you're going to get are also going to be equivalent. Okay, so that was the background. Now, how do you work with bulk compoundry? Well, the first version of this, due to Schultz-Balder's Kellendonk and Richter, realized that you could use the tuplets algebra that we came across before, and just motivate that in a slightly different way, that there's another way of thinking of the tuplets algebra, which you can get by looking at the unit disk. It's got a boundary circle, and then there's a Hardy space of functions on the circle, which is the subspace of functions on the circle, which are can be extended holomorphically into the disk. And there's an associated projection, bracket is positive energy projection, because that's what happens when you look at loop group theory. The pointwise multiplication action of the functions on the circle can be restricted down to the Hardy space, and it gives an action of the triplets algebra. So at the bottom you've got another way of thinking about the triplets algebra as a sort of compression of the functions on the circle. And what Gallandon, Richter and Schultz-Baldes did, I think I've got the date slightly wrong because there's an earlier paper in 2000. If you want to consider bulk and boundary of a material, then what you can do is you can take the boundary and you can sort of glue it to the bulk. And it's the triplets algebra which provides the glue in just the way that with the disk and the circle, that somehow the triplets algebra was sticking one onto the other. And so what I'm going to do is I'll call the boundary algebra E hat, the bulk algebra B hat, the triplets algebra. Well, there's a slight modification of the triplets algebra I had before, which builds in E hat the boundary as well. Since our boundaries are a bit more complicated than just a circle. And on the left, it doesn't matter if we tensor the boundary algebra with the compact operators, because that's not going to change the things up to Morita equivalence. And then we get a sequence, a sort of known sequence of these things, which shows how the triplets algebra glues things together. And there's also a Pimsner-Voiculescu sequence of algebraic K-groups. Whenever you've got one of these sequences, short exact sequences, you can build something like this. And so along the top we've got 0 K-groups, and then there on the bottom the 1 K-groups, and there are index maps linking the top and the bottom row. Doesn't go on it further because I'm dealing with complex K-theory, which has period 2.
What do you mean by boundary? Boundary of what?
Oh, well,
operator algebraic. Can you explain? Because just I know that behind all this work of Gallandon and Pimsner-Voiculescu there is some geometry, so maybe there is some object where you have really you can define a boundary.
Yeah, well, yes, in a sense I'll be coming to that.
Okay.
But I mean, in the laboratory, the bulk and the boundary is just, you know, you've got something like this as the bulk and as the boundary.
Yeah.
Okay, you can show that the triplets algebra in this particular case has the same K-theory. And well, apart from the fact I've missed a couple of hats off in the middle of this diagram, there's the sequence comes out in that kind of form, so that the 2 middle E's should also have hats on.
Why did you write a hat in the first place?
Because I wanted it
You're going to do it
to
twice.
be linked to another one, which is the answer to the other question. Or an answer. And one of the problems with this particular one is that the vertical arrows are given by index maps, and they're rather more difficult to handle than the ones which are horizontal, which are essentially sort of fairly straightforward. yeah, sorry. This is just to show you why I'm not doing real K-theory. Instead of having a hexagon, I'd have a ecosy tetragon of real K groups going around, so I didn't want to try and keep drawing those. In fact, there's a better way of doing the real K-theory anyway. Okay, now to motivate the next step, I want to just mention a not so well-known representation of the canonical commutation relations. I mean, normally what people know is the Schrödinger representation as functions on an L2 space, or the Fock-Arden-Siegel representation on an operator theoretically or on holomorphic functions. But there's also a lattice representation due to Cartier, which takes place on L2 sections of a line bundle over the torus of the phase spaces, or a double dimension. And it arises by taking the kind of classical phase space and then factoring out not just by the crystal lattice, but by the reciprocal lattice as well. I don't know why that isn't more used in solid state theory, but at least here it's useful motivation. And if we were just working in one dimension, what you'd then have is, I've represented the torus in the standard kind of way in the plane, so periodic horizontally and vertically. And the actual dimensions that you get is that that's the crystal size and that's the reciprocal lattice size. And you can flip those around with a sort of Fourier transform. And that has the advantage that it sort of turns pointwise multiplications into convolutions and pointwise evaluations to integrations, or the other way around, depending which way you do it. Well, actually, that's a slight exaggeration of what happens in detail, but that's the sort of idea. Now that sort of diagram appears in more or less any popular book on string theory which you read as T-duality in string theory physics. You also have tori, and it doesn't matter which way you think of it. So you, in string theory, you're doing interchanging momentum, winding number. And there's actually an added ingredient in string theory. There's a flux, which is a 3-4. So the work that is doing with Matin and Guochuan was trying to exploit this. And first of all, if we're going to exploit it, we want an algebraic version of this, which Evslin, Matin, and Peter Bouchner produced, I guess, 15 years ago. And in the algebraic theory, it's very simple, that the T-dual is taking a cross product of the algebra that you start with by a vector group. I've put down here slightly inaccurately the cross product continuous functions, a complex support from the vectors into the algebra you start with. Of course, you need to close that up, so that's just the pre-C-star algebra. And then I've given the multiplication, the adjoint style operation. And then that gives you this cross-product algebra. And if the lattice is acting trivially on the spectrum, then it's not doing anything to the geometry. So on the spectrum, you just have an action of the torus V over L. And that's a situation which occurs both in string theory and here. And there's a Takai-Takazaki T-duality. Very convenient that Takai and Takazaki both have names beginning with T. And that just says that if you do the procedure, well, first of all, once you've got the cross product algebra, there's an action of the dual group on that. And if you do the process again, taking the cross product and cross-producting it with the dual group, you get not quite back to the original algebra, but just the original algebra tensor with compact operators, which is Morita equivalent to the original algebra. So that's what actually makes this a genuine duality. Okay, the geometry. So if you were looking at sort of the situation a bit more geometrically, then you've got your bulk, your boundary, and what you can always do in these things, you can have a sort of interior algebra, the ideal of things which vanish on the boundary. And so the natural thing in geometry would be to write down a short exact sequence in which you have the interior going to the bulk and then going to the boundary. Now to put that into a more detailed C-star algebra thing, what I want to do is one more algebra, induced algebra, where you take the functions from, well, in this case I only need the reals into, say, the boundary algebra, and you put on a kind of periodicity condition corresponding to the lattice symmetries of the situation. And you give that a pointwise product and star operation. And what we're going to do is think of the bulk as being that induced algebra. And the reason I've only put in one dimension there is I'm thinking of the boundaries being like this, and there's just one transverse direction. And then the interior, I'm going to take either to be the continuous functions on the open unit interval into the algebra, or I can also think of it as the continuous functions vanishing at infinity on the reals, those things being the same. So if you start off with that interior algebra, you could always extend periodically and give functions in B, so you'd only get the functions which vanish on the boundary points. And therefore what you get is the exact sequence that you want, with the interior going to the bulk going to the boundary. And again, you'll have a Pimsner-Volkulescu exact hexagon of these K groups. And it's known, in fact, that this is another way of getting the same Pimsner-Volkulescu hexagon as before, but there's kind of a slightly different way of thinking about it, is that when the algebras are related by T-duality, then the hexagon that we're getting here is actually the same as the one that we got before, apart from some possible degree shifts. So let's just have a look at the geometrical version again. The interior algebra was function algebra from the reals to the boundary algebra. It's a suspension of E, so its K-theory is the same as that of E, apart from a degree shift. So that the hexagon that we got that way can be rewritten, replacing the i's with shifted e's. So that's the first step. We can rotate that. I just shifted it round and I get this one, which is beginning to look rather like the kind of hexagon that we had before. So now there's a matter of getting the correspondence between the physical and the geometrical picture. And I think I've probably got time to do this on the board because I think these kinds of calculations are probably better on. Does anybody have any? Would you rather have a switch to board or just doing it by slides? Okay, I'll carry on the slides. Okay, so the idea is I'm going to take the different algebras to be T-duals of the ones that the physical ones are going to be T-duals of the geometrical ones, where by physical ones I mean the ones with hats on them, by geometrical ones the ones without hats. And so I'm going to take E hat to be E cross-producted with a D minus 1 dimensional thing, so I'm thinking that the whole object is D-dimensional. So B hat will be B cross-product with R to the D, but the boundary is 1 dimension lower, so that just gets an R to the D minus 1. But the way the cross-product acts is going to be that it breaks down into the transverse real direction rest. And the action of the rest is going to be the same as the action on the boundary algebra. The action on the transverse direction is going to be the obvious thing that you get because the boundary, the bulk was the induced thing you got from the boundary, and there's a translation in that transverse direction which you can do in the induced algebra. Okay, so those are the things, and I want to make a connection with something I said before. So if I just look at the link between the bulk B hat and the E hat, I've got the B hat as a cross product. We know precisely that that cross product is B was an induced algebra, so we get down to induced algebra cross product with R to the D. R to the D broke up into R cross RD minus 1. The RD minus 1 commutes with this alpha, so we can bring it inside the inducing. And that means I'm inducing the E hat. And I've just got left over the cross product with R. And the point about that is that there's a theorem of Phil Green which says that if you've got that kind of situation, you induce something and you take a cross product, then it's essentially the same as if you didn't induce at all and just took the cross product with the subgroup that you induce from, up to tensoring with the compacts. So that's Morita equivalent to just taking A and cross-producting with the integers. And that means that the B hat, going all the way through, is Morita equivalent to the hatted boundary algebra cross-producted with Z, which is what is very often used in the kind of non-physical thing that you, somewhere or other you have the bulk being the boundary cross-producted with the integers. Okay, then we sort of finish things off by using Con's time isomorphism theorem. That there's a natural transformation of functors which takes you from kj of an algebra cross-producted with r to the d to kj plus d of the algebra A. And it's one of these remarkable things, because if the cross-product action was essentially trivial, then the left-hand side of that top yellow identity would be the suspension in the case of d equals 1. And the amazing thing is that it doesn't matter what you cross-product with, essentially. Well, there is a technical restriction, but not really relevant here. And that means that we can rewrite the kj of the hatted things in terms of shifted K-theory of the unhatted ones. And actually, there's Paschke wrote a more detailed version of bits of Cohn's theorem paper, which has a fairly explicit reconstruction of the triplets algebra. It's essentially there in Kohn as well, but less explicit. So using those results on shifting the K-theory, we can take the geometric Pinsner-Vokulescu hexagon, and we can turn it using Kohn-Tom and the Bott periodicity into a hexagon of the general form given in green down below. So essentially you can reconstruct the Schulz-Spalders-Kalendon-Richter version of what's going on with Balkan boundary into the geometric one, or vice versa. Yeah, I should perhaps, before we go on to this, just mention that there is a lot of growing evidence that if you've got these kind of physical situations, say you've got something like the quantum Hall effect, so you've got your system, your thing with a voltage and a transverse current and all that. But so essentially everything's happening on the boundary where you've got something sort of sprayed onto your sample. That actually the currents that flow in this thing are mostly along the edges. And so knowing what the relationship is between the bulk and the boundary is quite important. And that crops up an awful lot. So that was part of the motivation for the Kalendon-Richter-Schulz-Spalders work. And there's a lot more on these things. I was talking to somebody, I suppose about 8 or 9 months ago, who was working with a team in Germany who are busy preparing 4- and 5-dimensional materials. Well, how do you prepare a thing with more than, say, a 4-dimensional sample? The answer is you use internal degrees of freedom as sort of simulated extra dimensions. And you can set it up in such a way that the theory still applies exactly as though they were separate dimensions. And so they were interested in, amongst other things, looking at boundary effects in 4 dimensions. 3-dimensional boundary of a 4-dimensional object, or higher. I think they got up as far as 7. The only thing is that the simulated dimensions are quite small. These are actual lattice systems, and in the simulated extra dimensions, they sometimes only have as few as 4 points. So distinguishing what's bulk and what's boundary is a little bit problematic. Okay, so in string theory, you've also got this H flux. And given by a 3 form, and there's the Dixmuir-Doherty theorem, which tells you that given a locally compact space and a 3 form, then you can get a C-star algebra, continuous trace algebra, whose spectrum is the space and abstraction is 3 form. It's unique up to Morisi equivalence, so that all such algebras have the same representation theory. You can also think of this continuous trace algebra as being an algebra of sections of a compact operator bundle over the spectrum. In string theory, the Dixmuir-Doherty class gives a so-called H flux. Well, what about H flux in condensed matter? That doesn't seem to appear much. But there are some sort of vague possibilities. One of them is in screw dislocations in crystals. If you have a sort of nice crystal, say on the left, and you dislocate it, as shown on the right, and you take a path which goes around the screw dislocation, then you get a vertical jump. And that essentially extends the group of horizontal translations by some vertical ones and gives you an integer Heisenberg group. And those are known to arise as the T-duals of noncommutative algebras with flux. So one possibility is there. I don't think anybody's made any serious use of this, but and wild speculation. There is a classes of material called spin-races, and it was discovered, well, I guess now almost 10 years ago, that you have analogues of magnetic monopoles in such materials. And the point is, this thing's made up of lots of sort of tetrahedral configurations. And at each vertex there's a dipole either pointing in or out, and generally you should have 2 in and 2 out. But you can create anomalous regions where that's not the case. And in these Power-Kroll lattices, you can produce these things which have some of the properties of magnetic monopoles. I mean, there's a good sort of general feature that if something can't be discovered in CERN, then why not create it in your laboratory with a condensed matter sample? If you can't find magnetic monopoles out there, then you produce them. If it appears that neutrinos have a positive mass or mass 0, so that they're not discrete with Weyl's equations, you create some new Weyl fermions on the surfaces of condensed matter. Anyway, there are actually some obstacles. I mean, the thing is, it's known that the Dirac magnetic monopoles are described by 3 forms. So you might think the same thing happens here. There are some problems with that, but one can still speculate, and I think I shall stop at that point.
Questions or comments? Let's thank the speaker again.
Switch this off.